everybody, welcome back to Kosmos. One of the fascinating things about the history of horology is looking at how things used to be made in the early days and actually comparing them to the way things are done now. In reality, other than in the industrial process where hundreds of thousands or tens of thousands of things need to be made in succession, all nearly identical, the craft of horology simply hasn't changed a lot. Fundamentally, it is still the case of a person scraping away at a piece of metal with another piece of metal, or sometimes with a piece of stone. Many processes can be done very simply with the most rudimentary of tools. For example, turning, anecdotally, can be done using three heavy nails hammered into the workbench, forming a rudimentary set of turns with which you can turn very high precision staves and arbors as well as in any lathe. However, other processes are considered much more sophisticated. For example, it's often thought that a workshop would need quite a lot of considerable equipment in order to cut teeth. The ubiquitous and archetypal tool that is thought of as being required for wheel cutting is the wheel cutting engine. This is a very beautiful example of a wheel cutting engine, all made of iron with these brass locking nuts. And the main feature of this tool is the dividing plate. Now, looking at this dividing plate, we see that it's got rows of holes, and there's the primary, like the start point here, which you can see is a straight line, and then they kind of veer off because of various numbers of holes. With the selection of holes here, you'd be surprised at how many factors can be derived, and therefore, most watch wheels would be able to be cut with this very tool. Now, this is a small-sized example, and it is designed to be powered because you can see there's a pulley there. And all in all, this would have been a very expensive piece of equipment to own, and only the best workshops would have gone out of their way to acquire one when they became available. So the question is, how were watch and clock wheels cut? Or more specifically, how were the teeth cut before a machine of such sophistication came into existence? In autumn 2016, some friends and I ran an exhibition. On 500 years of horological wheel cutting. Now, in that exhibition we had a wheel engine, and the one we used was enormous, many times the size of this. It took two of us to carry it. So that was an antique wheel cutting engine, and in fact it was hand powered. So the chap who was operating it was cranking the cutter away by hand, and was pretty clapped out by the end of the day. I think it was hard work. Some of the other methods that were shown were electronic dividing of a lathe headstock and manual dividing of a lathe headstock. But it is the period before the rise of the wheel cutting engine that fascinates me most. So here I've got a couple of the blanks that we used in our exhibition, and in fact rather than crossing them out, one of our friends with a CNC engraver kind of gave a representation of the crossings of a wheel. And he drilled a little hole there so that these could be used as key rings or tags after the fact. And so there's a stack of these left over. And of course, the cut wheels were given to members of the public. It was my job to show how wheels were cut in antiquity. And really, that is the part that fascinates me most, because it shows exactly how simple hand tools can be used to create something as sophisticated as a clock wheel. Now, it wasn't until well into the 20th century that sheet material like this piece of brass I'm holding became freely available. Before that, parts made out of flat material would have been cast. So blanks would have been made of cast brass. Now, because cast brass has a very even and kind of loose grain, shall we say, to the metal structure, the castings would have been hammered on an anvil until they were about a third of their original thickness, is the rule of thumb. So I don't have the facility to show that, but if we just get a rough idea of the size. Right, so that would take me right to the very edge, which would be too close. So I'm going to come away from the edge in each direction somewhat. So there's my blank. It's not perfect. I've gone precariously close to the line in some places, but I don't like leaving very much to file away. You know, some workers like to leave, you know, 1/8 of an inch or whatever, but you know, it's as much trouble to file away from the line as it is, you know, pretty much right on the line. So why not leave the finishing to the minimum? In any event, we now have a blank as it may have been in the hands of any clockmaker going back 500, 600, 700 years. With a blank like this, how would a clockmaker, without access to a machine like the dividing engine, have marked off a required number of spaces along the edge of this disc, first of all, and secondly, how would he have cut teeth into that disc? Rewinding back from the development of the wheel cutting engine, we see this brass disc that was mentioned earlier. So this whole device is the engine, and this is the heart of it. Before the dividing engine came into being, most clockmakers would have possessed just this brass disc, and many of them would originally have had as part of their body a little loop by which they could hang this on a nail on the wall, or perhaps tie a piece of string through the loop and hang that on a nail. And very few original dividing discs or dividing plates survive, simply because it would have been recycled at some point or another in history to attach them to an engine. And so one sees very few extant with a little cast loop on the edge of the disc. Now, I don't have a loose dividing plate of this type, but what I do have is a dividing plate from one of my lathes. So this particular plate, I believe, is from my Shoblin. Now, it's not quite the right proportions, and I haven't prepared a mock-up because this isn't the object of the real object of the video. But if you imagine this being the dividing plate in the hand of the clockmaker, it would have had something like an arbor, a bit like this. So a bit of a handle with a spigot, with a nut or some method of fastening the blank down. And right in the end of that spigot there is a little center pop. Now you can see that these blanks have been made at such a size, yes, that they will fit that quite neatly. I should say the arbor was made of such a size that it would fit the blanks well, just neatly enough. And actually the bore there was designed to fit the dividing plate we were using at our exhibition, because we also had an original dividing plate. So that would have then been at one with the dividing plate. So the clockmaker would have had a pair of dividers. He would have then selected the row of holes that contained the number of teeth he wanted to make, or the required factor, and then just by eye get an approximate radius. So open the dividers far enough that if I were to strike an arc now, it would be more or less square to the edge of the work. And so if this were all neatly clamped down, you could see that you could make a scratch and then move along one space, make another scratch, move along one space, make another scratch, move along one space, make another scratch, and so on. You would therefore be left with a series of equally spaced scratches on the edge of your workpiece. Soon after, a development arose where the workpiece or the blank would still be clamped to the dividing plate, but a kind of strap was arranged to clamp everything down, and the strap had a movable arm that could be rotated, and so you could kind of match up with a little index mark in the end of the arm with the holes, and then use the arm as a rule to scribe the lines. So the arm basically swung around that center point, and that would allow you to scribe the lines, probably with a slightly greater accuracy. However, the earliest method of all uses almost no tools in order to do dividing. We can use the simplest geometry, the sort of thing that is done by 6-year-old school children. And I will scribe a slightly smaller circle now because oops. Now we must remember that clocks being made by these methods, although they're not high precision kind of astronomical clocks, were more than good enough and hardly improved for hundreds and hundreds of years, from the verge escapement and the recoil escapement, the kind of gear trains, were broadly as as good as what we're seeing here. It was only when we came into the very sensitive clocks, like those with the Graham deadbeat escapement, where it became a necessity to pay a lot of attention to the shape, the exact kind of scientific shape of the gear teeth. Now we need to decide how many spaces to create on this wheel. So how many teeth does the wheel want? I'm going to cheat slightly. First of all, I'm going to use a more modern pair of dividers because actually this pair is a little bit lumpy for this scale of work. So I'm going to use a more modern engineer's pair of dividers, a bit lighter, and the points are a bit finer. And I'm also going to cheat because I'm going to predetermine roughly the width of teeth that I am happy to work with for the sake of the video. And to preserve my sanity, I will make a mark so I can see where my start point is. We'll just make an arbitrary scratch. And then we'll go around. Now, I will just see roughly where we are with this stepping round process. That's 1, 2, 3-ish, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 27, 28, 29, 30, 31, 32. Okay, so that was very rough. And that was 32 spaces. I think let's make 31 because that's a legitimate number in horology. 32 isn't so common. 31 could be used for a calendar display, although calendar display would be sore teeth, and I think that I wouldn't like to show kind of triangular teeth. I'd like to show proper wheel teeth. So we'll open the dividers just ever so slightly, just a fraction, and then let's do it in earnest. 1, 2, 3, 29, 30, 31, 32. Okay, I'm well out. I'm an entire division over. Well, I've got one extra division in there, and then some. So I need to open it a bit more, but it's not really a lot because, you know, I have to open it 1/30 the space of the existing space, which you'd be surprised spread over such a big distance. One, 2, 3, 4, 5. You see, that's going to be too much. I'm already halfway between two divisions after only 5, so I'll crank it back ever so slightly. I'll try again. So you have to keep your wits about you when you're doing this, because the largest number of teeth, it's easy to begin to lose track which scratch you've already employed. 9, 10. That last division was very close to the end. I mean, unacceptable in wheel teeth terms, but it's a question of leaning on the dividers a bit harder in one direction or the other. So we'll have one last go. One, 2, 3, 4, 5, 6, 7. 8, 9, 10. 29, 30. Yay, 31. And I can assure you that the 31st line does lie exactly on the first line, and I prove that by putting the divider back in the 31st line and then starting at 1 again. So that is as near as damn it. So now we have 31 equally spaced divisions using no equipment whatsoever. This particular method I first saw on television a few years ago, demonstrated by Michael Wright. Now, Michael Wright used to be the curator of the Science Museum in London, and he'd made a study of antiquities and technology in antiquity, and he devoted his sitting room into a workshop, and I saw him step off a wheel like this, and I can't remember how many spaces he made. It was probably a lower number, like 8 or 10 or something, with triangular teeth, and then proceeded to file the triangular teeth. And so therefore, using very primitive tools, and you don't even need to use a pair of dividers as nice as this, you could probably get away with using incredibly crude tools and get a very precise measurement. So the next question is, how are the teeth themselves formed from a blank thus prepared? Well, that is the subject for the next video.